Have you tried Sumplete yet? If you haven't, you should try it. It's a fun little puzzle game. You have a square of numbers and you have sums that they're supposed to add up to. And so you have to cross out numbers until they add up to the sum. So you can see here they add up to 6. And I want to get 10 here, so I'm going to cross out the 1. And I want to get 7 here, so I'll cross out the 5. And ta-da, I've won. And you can do larger levels, like this 6x6 board. And eventually, at the highest level, where you go to 9x9, they add in double-digit numbers and positive and negative numbers. So it gets quite a bit harder and very, very challenging. Now, what's interesting about Sumpleat is the story behind it. This guy named Daniel Tate was playing with ChatGPT, and he asked, "Can you invent a logic puzzle similar to Sudoku that doesn't currently exist?" And ChatGPT gave him a couple options and eventually showed him this idea of sum delete. And you can see it's got some numbers and it has the sums. And Daniel said, "That sounds pretty good. Can you give me a playable version in HTML and JavaScript?" And so ChatGPT did. So this game that you're seeing here is entirely generated by ChatGPT. Now, there's some question about whether this was based on an existing game or not, and I'll put a link in the description below about that. But today we're not going to go too much into that because I don't actually know anything about the controversy one way or the other. But what I can tell you is by the time you get to the 9x9 level, this is a really hard game. And so when I see a really hard game like this, one of the things that occurs to me is we ought to write a solver for it. And that's what we're going to do today here on The Art of Software Development. All right, a couple ground rules just for the rest of the video. All the code that I'm writing is going to be in the GitHub repo that I have linked in the description. So if you have trouble following one of the lines or something, you can't read everything, just go there. This is not intended to be production quality code. It's trying to show the ideas, and it will work for as much as it needs to in the video. But if you were writing this in production, you would probably do more error handling and things like that. Some decisions I make, some of the design in this is not how I would probably do it in production quality code. It's how to explain it easier in a video. And finally, I'm going to use Java. But anything in Java that I feel like would be hard to understand for people who that's not their best language, I've skipped those features of Java, so I'm going to use some kind of common denominator of the language. Very, very quickly, let me review the rules of this. We have an n by n square with numbers in it. Each row has a sum it needs to add up to. Each column has a sum it has to add up to. And what you do is you cross off certain things and you circle other ones to add up to the sum. All right, let's start coding. So first off, I'm going to go ahead and write some code for the board. And it'll have a size, it'll have the matrix of data, and it'll have the sums. And just to be on the safe side, I'm going to add some assertions to board. All right, now I'm going to make a solution class that will be the solve version. So the board is the input, the solution will have the output. And the output I'm just going to store as characters for now. And how I'm going to store that is I'll have an X for anything that's crossed out, and an O for anything that's circled, and I'll just have a space for anything that's anything else. Now hopefully by the time we get the thing finished, there won't be any spaces, but at the beginning there'll be a lot. Let me go ahead and write something that initializes this now. Okay, so that just loops through and sets everything to a space. And now let's go ahead and make a solver class that will have both the board and the solution. And what I'm going to do is the constructor will take the board, but we'll own the solution for this. And the solver class should have a solve method. We'll leave it blank for now, but we'll write it. Okay, and let's start writing our main method. And I want to have a method for printing the solution. I've gone ahead and written that. It's you can look at the code if you're interested in it. It'll make a lot more sense once we see what the output format looks like. So here it is, and let me show you quickly what that output format's going to look like. All right, so the only thing left to do is how do we get the board set up? Well, I've got a couple just test boards that I made up, so I have some little functions for those. Let me put those in. So here I have a 3x3 board. Here I have a 6x6. Here I have a 9x9. These are ones that I just got from playing Sumpleat and just copied some to have some test data. And right now what we're going to do is we're going to just use the 3x3 until we get that solved, then we'll move on. So now let's just make sure everything runs. And it prints out an empty board because we don't do any solution stuff. All right, that's my first Git commit. I'm going to go ahead and do that, and then we'll start writing the solver. Let's start talking about how we might represent our intermediate state. If you start playing the game, pretty quickly you'll get to a situation like this. You have a row with the numbers 5, 5, 3, and 7, and the sum of that is supposed to add up to 10. And of course this could be a column instead of a row, but I've just drawn it as a row. So how can we get 10 from the numbers in the row? Well, we could circle 5 and 5 and cross out 3 and 7. Or we could cross out the 5s and circle 3 and 7. And that's it. That's all the different ways to get the required sum of 10. So we might be tempted to write something about 5 and 5 sum to 10 and 3 and 7 sum to 10. But it's actually a little more complicated than that. So let's look at a different example. So in this example, we're still trying to add up to 10. And to do that, we need to sum up two 5s. But it can be different pairs of 5s. The first two, the first and the last, or the last two. And so just saying 5 plus 5, the two 5s aren't distinguishable. So we need a way to distinguish which pair of 5s we're talking about. And the way to do that is use the indices. And you could imagine us writing out a bunch of equations like this, with different indices summing up to the row sum. Or alternately, we could just write the indices, and the equation could be just entirely implicit. And we'll need a way to talk about these things, and a way to code them up. So we'll need names for the classes we're going to have. So I'm going to call one of these sets an index set. And so right now I'm showing 3 index sets. This one, and this one. Index set is one of the basic data structures we'll use. And there's another closely related one. If we combine the 3 possible index sets we have, let's say we just put them in a list, then we have a list of all the possible solutions to this row. So this thing, the list of index sets that represent the possible solutions of a row, that needs a name. I was originally going to call it possible solutions, but that might be confusing because you might think I mean possible solutions of the whole puzzle, and it's really just possible solutions of one row. So maybe we could call it possible row solutions. But we'll want to do the same thing for column, and I don't want to have 2 different data structures if I can help it. So I'm going to call it possible RC solutions, where R and C are row and column, but I probably won't type them out. I'll probably just write RC. And when we get back to code, we're going to want to look at each row and generate all possible row solutions, and look at each column and generate all possible column solutions, and store those somewhere. Let's go do that now. So I'm going to start by creating an index set class. And I'm going to do something here that's not great object-oriented programming, but here's what I'm going to do. So I'm going to make this inherit from hash set of integer. Now, if I were in a different language, C or C++ or Go, I would just use a type def here because that's what I'm really trying to get at. But as far as I know, there's not an easy way to do that in Java, so what I'm doing is just inheriting from it. Now, this is not a great example of inheritance. Don't do this in your own code, but this will let us use the word index set whenever we mean a hash set of integers. And now I'm going to go ahead and make my possible RC solutions class. And we're going to do the same kind of thing. And if you're wondering why I'm using a list here instead of a set, pretty much it's just for making this video a little easier to understand. Because if I talk about the set, you know it always means the index set. If I talk about the list, you know it means this possible RC solutions. So in our solver, let's go ahead and add these constraints. So what I'm going to do is I'm going to make row and column constraints. And I need to initialize those in my constructor. And I want to fill them in. I'm just going to do row for now. We'll come back and do column in a second. And so obviously the problem is I haven't defined this function, so let's go ahead and fill that in. So how are we going to do this? Well, roughly what I'm going to do is I'm going to make a list of all possible subsets. And then I'm going to filter out so that they match the sum. All right, so I want to generate all possible subsets of size n, and it's actually not super hard to do that. Now, you might think, well, wait a minute, is that wasteful? Should you be more clever? Should you combine it? The biggest n we're going to use here is 9. There are 2 to the 9 possible subsets, which is 512. That's a big number if I'm writing them out by hand, but for a computer, that's a tiny number. So I'm just going to go ahead and create such a function. And I'm going to make it a static method on possible RC solutions. All right, and so how do we create that function? Let me just go ahead and do that. And so what I'm going to do is I'm going to iterate through, and in each round, I'm going to take all the sets I've generated so far and add the next element onto half of them and add the set without those to the next one. So it may make more sense just to see that. Okay, so what I want to do is I want to have a constructor for index set that will take an index set and copy it. There is such a thing for array list, but I need to expose that because that doesn't exist. Let me jump in and do that so this goes away. And I think I actually need both of these. And so what this does when you pass it a set, it copies that. So we're not dealing with like a reference or something, we're dealing with a copy. And that's it, except we need to return the result. So does this make sense what it's doing? It loops through and copies all the sets and then adds new sets that do have the I. This is just going to generate all the to the n possibilities. Oh, and I do have one mistake. All right, so back here, let's filter out the ones we care about. And how do we do that? Well, we just have to calculate the sum. And then if it's equal to the row sum, we add it. All right, now I need to do the same exact thing for columns. And here's one of those things making it easier to explain and harder to code. I'm going to actually make a copy of this that's called Get Possible Solutions for Column. Because essentially what I need to do is I need to switch these two indices here. So I'm just going to go ahead and copy that and code it up. There's nothing profound about what I'm doing, and if you're doing this at home, you can probably come up with a better way to do this, but for the purpose of the video, I'm just going to copy and paste. And again, it seems silly to me to do all this just to be able to switch the indices and that column sums. But if I do anything different, the code gets really abstract, and I didn't really want to do that for this video. Okay, so what we have now is that we generated 2 to the n possible subsets that could possibly satisfy, calculated the sum for each one, figures which ones actually match the sum, and now we have these constraints that says the possible RC solutions for each row are these, and you get a set like we had in the slides. And so this is the next commit in Git. Let's look at the big picture of what we're planning to do, then we'll start coding it up. I want to get the basic idea here, then we'll deal with more subcases as we go on. So we'll start with the game, numbers in the board plus row and column sums. We added indices to help us reason about this. Then we add all the index sets that give us possible solutions to the rows and the columns. What we're going to do is pick one of the rows or the columns. Let's say this one. And it only has one possible answer, so that has to be the solution for that row. So we'll circle and cross things off. That's one kind of operation, which goes from constraints to the board. Now let's look at it the other way around. When we circle or cross things off from the board, that will affect the constraints on that row and that column. For example, in this one, there's one of the sets that doesn't include 8, so that can't be in the solution, so we'll cross it out. Don't worry if you didn't follow the specifics of that. Just know that circling or crossing out a cell means we need to recheck the constraints at that row and column. We've talked about a lot, so let's organize it. First, we'll be reevaluating the constraints for one row or one column. Sometimes we'll be circling a cell, sometimes we'll be crossing out a cell. Let's make an abstraction for all these kinds of things. I'm going to call it an operation. And operation will be a superclass of these 3 classes when we eventually implement them. And I'm worried about how we're going to do the control flow because there's a lot of back and forth. So what I'm going to do is I'm going to have just a to-do queue, and it will be a queue of operations. And we'll put some operations in, and our main solver will just pop an operation off and execute it. And executing it may cause us to have to do more operations, in which case we'll just put those into the queue, and we'll just loop like this forever until we finish the queue. That's the very high level of what we're going to try to do. Let's move to code, and we'll get into more details as we get there. Okay, let's start coding this up, and there's a lot, so it may be a little bit confusing, but let's start somewhere. And we know we had this thing called an operation, so let's do that. I'm going to make an interface, not any particular reason, but that's what I'm going to do. And typically an interface has a method. Presumably this will have a method, but I'm not sure what to call it yet, so I'm going to just wait on that. And we said that in the solver, we wanted to have a queue of operations. And up here in our constructor, let's initialize that. And you see I'm initializing it to a linked list. In Java, Q is abstract and you can't do anything with it, so you have to have a concrete class. Okay, so in our solve method, you remember our solve method, we're supposed to do something. So what we're going to do is we're going to repeatedly pop an operation and execute it. And of course, in Java, it's not called pop, it's called pull because of course. And I guess we could call this execute. Maybe we could call it apply. Let's just call it execute. And it should take the solver as a parameter because it's going to work on the solver state. Okay. Cool. So now we need to start with something. Let's go through and do the example I said. And we'll fill in some things where we leave to-dos, but we'll start there. So what I'm going to do is for each row, I'm going to add an operation. And it'll be a reevaluate row operation. That takes the row. Oops. So let's go ahead and make up such a class. And we said this needed a row. Let's go ahead and add that in. Let me try spelling it right. All right, and what should this do? Well, what we said is let's look at the constraint for that row. And the example we had on the slides was where there was exactly one solution. So let's only solve that case for now, and we'll come back to all others. Okay, and so what did we do if there was exactly one solution? Well, then we knew what to do because that means that there's only one index set. And so then what we want to do is go through the row and circle or cross out everything. So for every index, we'll either circle something or cross it out. And actually, I'm saying circle column or cross out column. I actually mean cell. All right, so what does it mean to circle or cross something out? Well, we need to circle or cross out operation. And this should apply to a cell. So we don't actually have a cell, so let's go ahead and make a cell. And cell is just a row and a column. I'll go ahead and do final. If you're not a Java person, final means something that you can set once and then never again, so it's kind of a constant. That just makes this class immutable. Circle operation needs a cell. And cross-out operation is going to do the same thing. All right, so to circle the cell, what that means is we make a new operation and add it where we wanted to. So what we need to do is solver.todoq.add new circle operation, new cell, row, comma, column. And then the crossout one, it's the same thing, except we want a crossout operation. And you know what? I'm going to copy my not implemented and move that up to here and here. All right, so a circle operation, the first thing we want to do is we want to circle this in the board. Sorry, not in the board, in the solution. And circling it, we said, is just putting an O there. What did I like that? Okay, and then we need to reevaluate the column, the row and the column. All right, and I can tell you right now, we're actually going to need a reevaluate column operation as well. So let me go ahead and just make that. And again, this is kind of silly. It's just because rows and columns aren't the same, and there's probably a way to deal with that, but I haven't. But actually, now that I have that, let me go ahead and add that in the solver. Okay, so just what we're doing here is when we first set up the solver, we pre-pack it with a bunch of reevaluate operations. So look at each row, look at each column, see what you can do. Okay, and back in the operations, we now have a circle operation. There's one thing that, I forgot to add the column. Let me do that. So there's one problem here, and I don't know if you can see it. If I ran it, you probably would see it pretty quickly. This will get me into an infinite loop that when I evaluate the row, it circles some things. When I circle the things, it evaluates the row. So what I want to do is have it only do this if it's not already been done. So I'm actually not sure. Let me see. Let me make this an inline variable. So if it's already done, we're fine. So let's see. If there's nothing there, we're good. If it's already done, it's just a no op. And the other possibility is we've already crossed this out and now we're circling it. So that shouldn't be a runtime exception that it's not implemented. That should be like a bad thing. Okay, does that look good? So if the current state doesn't have anything, we set it to O, which is how we're circling something, and then we reevaluate the row and the column. Okay, that looks reasonable to me. So let's go ahead and do the same thing for the crossout operation. So actually, before we reevaluate, we need to change the constraints to reflect the circling. And I'm not sure it's clear what that would mean without kind of walking through it. So let's walk through that first. Let's go back to our earlier example. Remember that it had three possible solutions. So there are three possible index sets. And the constraint of type possible RC solutions is just the list of those three index sets. Now suppose we're evaluating something else and it tells us to cross off one of the positions, say this one. Well, that rules out a bunch of possibilities because they're no longer consistent with what we know. So we can zap those index sets. And we'll cross them out in the list of possible solutions too. If we look at exactly what happened, we crossed out index 2, so that means we have to remove any possibility that contains index 2. Circling is the opposite. If we circle index 2, we have to remove any possibility that doesn't contain index 2. So let's go ahead and put that in code now. All right, so what does this look like? We're going to say solver.rowConstraints subcell.row. And if we circle, I'm going to define something called filter width. And we'll take the index of cell.column. So what is this thing going to mean? This is going to say, go through the row constraint. The row constraint, remember, is a list of index sets, and we're going to filter it to only those index sets with this column in them. And it's red because I haven't implemented it yet. But then we need to do the same thing with the column constraints. And now I'll do the same thing in the crossout operation. Except here, instead of filter with, I want to filter without. All right, let's go ahead and implement filter with. I know I said I wasn't going to use the Java functional programming primitives, but I am here because it's a one-liner if I do that. So filter with is remove sets if the set does not contain the index. Filter without is remove if the set does contain the index. So if you don't understand exactly how this syntax works, don't worry about it. Just realize that this is getting rid of any set that contains the index. This one is getting rid of any set that does not contain the index. And so just like that, I think we're ready to run and we should get an answer. And the answer is bad state. Fixing those two, let's try again. Okay, so we have a solution for this one. Let's go back to the slide and I'll go ahead and apply that solution. We'll see if it makes sense. Here's the 3x3 board from the code, just prettied up. And here's the output of the program. So let's overlay the X's and O's onto the board. And it works out nicely. You can verify that the sums all match. And this is the next Git commit if you're following along with Git. So are we done? Well, not quite. I'm going to come back here, and for reasons that I'll explain later, I'm going to skip over the 6x6 board and change it directly to 9x9. And if I run that, we get an exception and not implemented. Okay, what did we not implement? We didn't implement the case where the row size is not equal to 1. So what can we do if there isn't a single solution? Well, sometimes the answer will be nothing, so we shouldn't throw that exception in that case. And we just have to skip that constraint and move on. But sometimes we can do things. Back to our favorite example. Notice the set of possible solutions has multiple elements. So this is definitely not the one index set case. But notice that in all of the possible solutions, 7 is crossed out. So that means we can cross 7 out. Another way to say this, if we take the list of all possible solutions and take the union of all the sets in that list, that'll give us a set. Here that set is 0, 1, 2. That's the set of indices that are contained in some possible solution. Any index that's not in this union isn't in any possible solution and can be crossed out. And you're probably thinking, if we have a union rule, there must be an intersection rule too, right? And sure enough, there is. Let's see it. This looks like our favorite example, but now we have a different sum, which means we have different index sets and a different set of possible solutions. And all of them have 7 circled, or in other words, the intersection of all the sets is 3. So we can circle index 3, we can circle the 7. So let's go back to the code and implement these 2 ideas. So I'm going to start by implementing union and index, and I'm going to do that as static methods on index set. So there's union. And there's intersection. Union is pretty easy. You just add all the sets into a new set, and that's the result. Intersection, we're going to start with the first element and successively remove things. We retain all, removes everything that isn't in the set, which is kind of, a double negative or something like that. But that's how intersection works. So now let's go to our row operation. And let's maybe start with the intersection. Okay, that's pretty straightforward. The union is going to be similar, but a little bit different. Except what we want here is anything that isn't in the union, so we have to explicitly iterate over this. Now there's one thing that isn't entirely obvious, but I'm going to go ahead and do anyway. Notice that we checked if the size was 1 or else. Well, the intersection assumed that it was greater than 1 because we used the first element for doing the intersection. So I'm going to make a separate case for if the size is 0 and just throw an exception. And so let's just be clear about what this would mean. It's possible that you could have the empty set would be a possible solution. In that case, the list of possible RC solutions would have a set in it, and the set would have size 0. That's not what this is saying. That's saying there are no sets, which means the empty set isn't a solution either. So what that would be, for example, let's say you have 2, 2, 2, and you're trying to sum up to 5. There's no combination of even numbers that will sum up to an odd number. So that would be something where this is not possible. The other thing we have to do is copy and paste this and change it for columns. So I'll go ahead and do that now. Okay, we're all done. So let's run the 9x9 and see what happens. And it looks like we have an answer, so let's go ahead and verify that that answer works correctly. Here's the 9x9 board, and here's the overlay. You can see how hard it is to solve this. It's hard just to verify the various sums in your head. But anyhow, it checks out, unless I made typos in making the slide. The actual results check. And of course, there's a git commit corresponding to this point. And now we come to the 6x6 board. Remember how we skipped it before and I said I'd explain later? Well, here's the board, and here's the solution we get. Wait, what? There are unfilled spots on it. If you look at it, each row and each column that has blanks has two equally good possibilities. Another way of saying that is there isn't a unique solution to this puzzle. There are two. So our constraint solver resolved everything it could, but the solution is under-constrained. So what do we do? Well, first we need to detect this case. The way to do that is to check at the very end of the solve loop to see if there are any unsolved squares. If there are, we can pick one of them, say the first one, and try circling it and see if we get a solution. Then we try crossing it out and see if that gets a solution. In a case like the one here with the 6x6, we'll get a solution in either case. I'm not 100% sure that's always true. It may be that one way works and the other doesn't. In that case, we'll only get one of the two. Okay, so let's finish this up. So here's the solve loop, and the problem we saw was that we got to the end of this without an actual solution. So let's detect that case. What I'm going to do is I'm going to write something in the solution that will check if we get that case. And actually, let's just go to solution first, and let's write that. To just be clever about it, I'm going to loop through and see if there's anything that's a space. And if there is, I'll just return the coordinates of that as a cell. And if there isn't, I'll just return null. So let me code that. Okay, so there's code for that. And now let's put something here. And if there is a non-null value here, then we have to do the logic I just described. So I'm going to use try catches here because if something doesn't work, it should throw one of the various exceptions we've done. And you know what? The first thing we need to do is we need to make a duplicate of the solver state. So I'm going to make a new constructor that will copy the solver. But actually, that's not quite right because these are just copies. I actually need to clone these things. And so the one trick is other solution. I actually need to clone the other solution, and there isn't a method for that, so I'm going to have to write one. All right, so now we get back to the logic. All right, let's try first off circling the thing. And remember, this is calling the constructor that copies everything. And if we throw an exception, we're just going to ignore it and because we just want to go on. And now we want to do exactly the same thing, but instead of circling it, we want to cross it off. And just for kicks, I'm going to move this assertion to the end. So it shouldn't be the case that we ever get here. If we get here, it means that we failed to find any solution. But now with that in place, let's go to our main. And let's change it to the 6x6 board. And when we run this, it should give us a solution. And you can see, yeah, there are no more spaces in it. So that worked. All right, once again, this will go into Git in the last commit. This is the full thing. Everything, all the cases should be solved at this point. I hope you've enjoyed this video. Please like and subscribe, and let me know in the comments what you think. Was this easy to follow? Are there questions? Are there things that I should have explained differently? And if you need me, I'll be playing Sumpleat.